Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Most profitable path in a tree, Leetcode 2467. If you are new to the channel, consider subscribing. I try to make daily videos on the problems related to data structures and algorithm, including detailed explanations, optimized solutions, and step-by-step walkthroughs to help you improve your coding skills. Now to the problem. In this problem, we are given undirected tree with n nodes labeled from 0 to n-1 rooted at node 0. For example, here n is equal to 5 and we are given nodes from 0 to 4 rooted at node 0, and we are given a 2D integer array edges of length n-1 where edges I indicates that there is an edge between the nodes AI and BI in the tree, and at every node I there is a gate which when opened results in the penalty or the cash reward determined by the given array of even integers amount, where if the ith amount is negative, it represents a price that must be paid to open the gate at node I. But if it is positive, it represents a cash reward obtained on opening the gate at node I. At the beginning, Alice is at node 0 and Bob is at any given node, Bob other than 0. This is what is mentioned in the constraint, that Bob lies between 1 and n but never 0. For example, here Alice starts at node 0 and Bob starts at Bob equal to 3. And now they have to play the following game. At every second, Alice and Bob each move to an adjacent node. Alice moves towards some leaf node while Bob moves towards node 0. For every node along their path, Alice and Bob either spend the money to open the gate at that node or accept the reward. Note that if the gate is already open, no price will be required, nor will there be any cash reward. If Alice and Bob reach the node simultaneously, they share the penalty or reward for opening the gate there. In other words, if the price to open the gate is C, then Alice and Bob will pay C by 2 each. Similarly, if the reward at gate is C, both of them receive C by 2 each. So because there is a possibility of division by 2, to simplify the division, they have given amount as even integers. If Alice reaches a leaf node, she stops moving. Similarly, if Bob reaches node 0, he stops moving. Note that these events are independent of each other. And in the end, we have to return the maximum net income Alice can have if she travels towards the optimal leaf node. Now let's look at the example to understand the problem better. Alice is initially at node 0 and Bob starts at given node 3. At time equal to 0, Alice goes from 0 to 1, but she has to pay the penalty of -2 to open the gate 0. Similarly, at the same time, Bob moves from 3 to 1 and he must have paid the penalty of -4 for opening this gate. Now, both of them reach simultaneously at node 1. So now, when they move forward, they will open the gate at door 1 together and share the reward, which is equal to 4. So now, the reward collected by Alice and Bob will be 4 by 2, that is 2 each. Now, Alice has two paths. Either she can go to this path or she can go to this path. So if she goes to leaf node 2, she will collect the reward as 2 for opening the gate 2. And since this is a leaf node, she will stop her game and the total profit she can collect from going from node 0 to 1 to 2 will be equal to 2. But if she goes to node 3 instead, then she will be paying penalty of 0 this time because Bob has already opened this door. And then she goes to node 4 and collects a reward of 6 for opening this gate. And now, since this is also a leaf node, she stops and the total profit she can get by following the path from 0 to 1 to 3 to 4 will be 6. And in any case, Bob will also continue with his path and reach node 0 where he needs to stop his game. And now we have to return the maximum net income Alice can collect. So it will be 6 in this case and hence that will be our answer. The input provides the edges of a tree as a 2D array. To facilitate Alice and Bob to move along the tree, we convert these edges to adjacency list representation because this data structure enables efficient traversals in both directions. So, Alice moves from the root node 0 to the leaves, and Bob moves from his starting point to the root. So this is how our adjacency list will look. Node 0 has node 1 adjacent to it. Node 1 has 0, 2 and 3 as the adjacent nodes. Nodes 2 and 4 have 1 and 3 as the adjacent nodes respectively, and node 3 has nodes 1 and 4 adjacent to it. Now, to traverse this tree and explore all paths, we can either use DFS or BFS. For Alice, DFS is the preferred choice because DFS naturally explores all paths to the leaf nodes, which aligns with Alice's goal of finding the optimal path that maximizes her income. However, BFS focuses on exploring the nodes level by level, which is better suited for shortest path problems, but less effective for evaluating cumulative income along paths to leaves. Thus, we use DFS as it efficiently handles Alice's objective in this problem. Now for Bob, BFS could also be a valid choice, but DFS works just as well. Since the input graph is a tree, that implies that the graph has no cycles. This simplifies our problem because in a tree, there is always a unique path between any two nodes. This guarantees that when Bob moves from his starting point to the root node 0, his movement is deterministic and can be computed without any ambiguity. Additionally, as there are no cycles, we don't need to handle the cases to deal with infinite cycles or logic for detecting overlaps in the path. So we can use DFS traversal for Bob as well. Now Alice's traversal involves exploring multiple paths from root node 0 to all possible leaf nodes. For example, in this given tree with two leaf nodes 2 and 4, Alice will evaluate two paths 0, 1, 2 or 0, 1, 3, 4. However, Bob's movement is simpler. Bob starts at the given starting node, in this case 3, and follows a unique path to the root node in a straightforward way. But that won't be enough because how would we know in case of an overlapping path between Bob and Alice who opens the gate in the node first? Is it Alice or Bob, or do they do it jointly? And based on that, Alice or Bob will generate their income or expense accordingly. So we also need to track the movement in time. So we need to compute when Bob arrives at each node along with his path so that we compare Alice and Bob's arrival time at every node and determine how their income or expense is split at nodes where they meet at the same time. Let's store it in the hash map called Bob time, and during the DFS we will record Bob's arrival time at each node in Bob time. So now let's see this in action. So Bob starts at node 3 at time equal to 0 and has 1 and 4 as their two adjacent nodes. Suppose Bob decides to move to node 4 and reaches there at time equal to 1, but it is a leaf node and after that we won't find the node 0. So this path will be discarded. Hence Bob backtracks to node 3 and now goes to node 1 and reaches there at time equal to 1. From node 1, Bob can either go to node 0 or node 2. Suppose Bob goes to node 2 and reaches there at t equal to 2, but that is also a leaf node and doesn't leads to node 0. So we backtrack and come back to node 1 and from here explore node 0 and reach there at time equal to 2, and this is our destination node. So our DFS stops and now we have a complete time map for Bob. And note that the time map for Bob does not contain nodes like 2 and 4 which are not part of Bob's path to root node. And now we can simulate Alice's movement. Alice starts from node 0 and tries to find the optimal leaf node that maximizes her net income using a DFS for Alice. So we can keep track of Alice's current income along with the time as she moves down to the leaf node. And now we have 4 cases of interactions possible between Alice and Bob. Case 1 can be that Alice visits a node which Bob will never go, like node 2, as it is out of Bob's path. So this is the simplest case, and here Alice gains or loses the full amount at that node. Case 2 can be that Alice reaches the node before Bob, and here again Alice gains or loses the full amount to open the gate at that node. Case 3 can be that Alice and Bob arrive at the node simultaneously, and in this case Alice and Bob share the amount equally. And finally, the case 4 can be that Bob reaches the node first In this case, Alice's income won't change. And based on these cases, we will calculate Alice's net income. And once she reaches a leaf node, we will update Alice's maximum income recorded for any path. But now the question is, how do we know if we have reached a leaf node? Unlike binary tree, where the leaf nodes will have left and right references as null, here leaf nodes have one node adjacent to them. But that is also true for node 0, so we should exclude it. So if a node has only one neighbor and the value is not equal to 0, it is a leaf node. So each time Alice reaches a leaf node, she calculates her total income for that path to update her maximum income. Now let's see this in action. So Alice starts at node 0. Initially, her time and income both are equal to 0, and Bob here reaches at time equal to 2. So she reaches here first and hence opens the door and gets the amount equal to -2. So now her income becomes 0 minus 2 equal to -2, and she has explored the node 0 at time equal to 0. Now node 0 has only one neighbor, that is node 1. So only node she can go from node 0 is to node 1. So she visits it and she reaches here at time equal to 1, and Bob here reaches at time equal to 1 as well. So they reach here simultaneously. Hence they split the income, and now her income becomes -2 plus 2, that is equal to 0. From this point, she can either go to node 2 or node 3. Suppose she goes to node 2 and she reaches here at t equal to 2, and Bob never reaches here. So she will collect the whole amount. So now her income becomes I equal to 2. And since this is a leaf node, we will set our maximum income to 2. And now we are done with this path. So we backtrack. So now only path she can go from this point is go to node 3. And here Bob reaches at time equal to 0 and Alice reaches here at time equal to 2. So she can't collect any part of the amount from this node. So her income stays 0. And then she goes to node 4 and Bob doesn't go to this node and reaches here at time equal to 3. But Bob never comes here. So she collects the whole amount from node 4 and now her income becomes 6. And this is also a leaf node. So we check if 6 is the maximum income. So we take maximum of 2 or 6. So now Alice's maximum income becomes 6. And now we have visited all the nodes. And how do we know that? In DFS, we use the visited set to keep track of visited nodes. So once we have visited all the nodes, the DFS terminates naturally as there are no unvisited neighbors left to explore. Now in terms of time complexity, it will be O of n, where n is number of nodes in the tree, because first we are constructing the adjacency list, which takes O of n time for n minus 1 edges. Then we run the DFS twice, first for Alice, then for Bob, which takes O of v plus e time, where v is number of nodes and e is number of edges, which are equal to n and n minus 1 respectively. So it will be O of n plus n minus 1, which is equivalent to O of n. So overall time complexity will be O of n. And in terms of space complexity, it will be O of n as well, because we require O of n space to store adjacency list, timing map for Bob, and visited set for the DFS. And in the worst case, recursion stack will also require O of n space in case the tree is queued. Now let's jump into the code part. First, let's initialize n as the number of nodes in the tree based on the amount array. Now let's create the adjacency list from the given edges. To simplify the code and avoid passing common variables like tree to the DFS functions, we can encapsulate them as class level attributes. This way we only pass parameters directly relevant to the recursive logic of the DFS methods. So now let's create the adjacency list for the tree as a class level attribute. Now let's initialize this tree, and then let's initialize the adjacency list for each node. And then we can build a tree from the given edges by adding the edge to both adjacency lists, since it is an undirected graph. Now let's perform the DFS for Bob. But before that, first let's initialize the map Bob time to store Bob's arrival time. Let's also initialize the array to track the visited nodes during Bob's and Alice's DFS traversal. Now let's perform the DFS with the starting point as Bob and initial time as 0. Now let's quickly define the DFS for Bob. First let's record the time for the current node and mark the current node as visited. Then we check for the base case, that is, if we have reached the destination root node equal to 0, then we will return true. Otherwise, we will recursively explore all the unvisited neighbors of the current node with the updated time as time plus 1 in search for the root node 0. If we find it, then we will return true. But if we can't, we will remove the current node's time from the bob time and return false. Now let's perform the DFS for Alice. But before that, let's store the amount array as a class level variable along with our answer max income for easy access to DFS for Alice. Let's also reset the visited array for Alice's DFS. And now we can start the DFS starting with the root node 0 with initial start time and income as 0. And once our DFS is complete, we would have calculated the maximum income that Alice can collect, which we can return now. Now let's define the DFS for Alice. First, let's mark the current node as visited to avoid revisiting the same node again. Now we will check if the Bob will not visit the current node or Alice reaches it before Bob, then Alice gains or loses the full amount at this node. Otherwise, if Alice and Bob arrive at the node simultaneously, Alice gains or loses half the amount at this node. And now we check if the current node is leaf node. That is, if a node only has one neighbor excluding the root 0, we will update the max income with the current income. Otherwise, we will recursively explore all the unvisited neighbors of the current node with the updated time and income, exploring the next possible paths. Now we are done, so let's submit this code. Awesome. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.